Okay, good evening everyone. We will start the today's session of computational science in engineering. So this week, professor discussed about the accuracy and how to find the roots for the equations, and then order of convergence and some related things for determining the root. So we will solve some of the problems today, and mostly your doubts will get clear. Okay, so the first question. One second. Okay, so the first question is the error to estimate the first derivative of the following function at x equal to 0.5. One second. Okay, at x equal to 0.5 using the forward difference approximation using the step size of 0.5 will be. Okay, so the function is given, and we want to find how much is the difference between the exact derivative and the approximated derivative. Okay, so if you see the f of x is equal to minus 0.1 x raised to 4 minus 0.15 x cube minus 0.5 x square minus 0.25 x and plus 1.25. Okay, so this is the function, and we can differentiate this directly with x. So if we differentiate, it will be minus 0.4x cube minus 0.45 x square minus 1 into x minus 0.25. Okay, and we want to find at x is equal to 0.5. so f dash at 0.5 is equal to minus 0.4 0.5 cube minus 0.45 0.5 square minus 0.5 minus 0.25. Okay, so we can determine this 0.4 minus 0.4 into 0.5 raised to 3 minus 0.45 minus 0.45 into 0.5 square minus 0.5 minus 0.25. Okay, so the answer is minus 0.9125. Okay, so we got this is exact, or we can say true value of the derivative. Now we will find the approximate. So in order to find the approximate value, what we will do is we'll use the, let's say at I location we want to find out. So what we can do is we can take the forward difference at xi and divide by step size, and that is nothing but f of xi plus h minus f of xi divided by h. And if we go back we can see that the step size is given to be 0.5. Okay. So what we want is, so x we want to be 0.5, so we have to find f of 0.5 here, and f of 0.5 plus h. So xi is equal to let's say 0.5, and h is also 0.5, and whole divided by 0.5. Okay, so we want f of 1 minus f of 0.5 divided by 0.5. Okay, so this will give the approximate value for f dash at 0.5. Okay, so we'll find out that, and if you see, it needs f at 1 and f at the function value at 0.5. So first we will find out the function at 1. So if we substitute 1 into this expression, so it will be minus 0.1 minus 0.515 minus 0.5 minus 0.25 and plus 1.25. Okay, so this will give one answer, and then this, if you substitute this 0.5 in this, so we will get the value at f at 0.5, which is minus 0.5. Sorry. This is 0.5 raised to 4 minus 0.15 0.5 cube minus 0.5 0.5 square. Okay, and minus 0.25 0.5 plus 0.5 only, and plus 1.25. Okay, so if we compute this, so I will calculate this using some it will be easier to compute this way, which will be minus 0.1 into x raised to 5 minus 0.1 x raised to 4. Okay, minus 0.15 into x raised to 3 minus 0.5 x square 0.5 into x square minus 0.25 x plus 1.25. Okay, so 1.25 minus 0.25 minus 0.5 minus 1.5 and minus 7. Okay, so powers are 4, 3, 2, 1. Okay, so this is nothing but just I wrote the function. We want to compute this function value at 1. It is equivalent to substituting like computing this first expression, and this value is 0.25. Okay, and next is 0.5. so f of 0.5 is 0.975. Okay, so we want f dash at 0.5, which is nothing but f of 1 minus f of 0.5 divided by 0.5. So we'll use 0.25 minus minus 0.975 divided by 0.5. Okay, so this we can compute here. So what we want is f of 1, which is already we find out, f of 0.5 divided by 0.5. Okay, so we got minus 1.45. Okay, so this is the approximate value we have. This is the approximation that we determined. So we'll say this f approx, and this value is f true. Okay. So error is nothing but f of true minus f of approx. So f true is minus 0.9125. Okay, and then the approximated is minus 1.45. Okay, so if we do the subtraction, minus 0.9125 plus 1.45. Okay, so 0.5375. And what we want is percentage error. So percentage error is nothing but that error we have divided by we'll use true value of the function, and we'll take mod into 100. So it will be 0.5375. f true is 0.9125, and we are taking mod, so we don't need to take minus sign. 100. Okay, so we'll compute this 0.5375 divided by 0.9125, 0.9125 into 100. Okay, so this is the error, 58.9%. Okay, so percentage error is 58.9. Okay. So the percentage error is 58.9, and if we see the option, the A option is correct. Okay, so we will go to next question. Okay, the next question is the one second. The next question is the correct forward difference approximation of the first derivative will be. So we just solved the problem where we find out that okay, instead of writing already options are there, so we can see from here. So this first option computes the derivative. Let's say this is I is not ready. So this is the ith location. So we are taking the first the next term. So if we have, let's say, xi and xi plus 1, and the function value here and here is known. So if you want to compute the slope of this, which is nothing but given by f dash is equal to, so if we see this delta y by delta x, and this is first forward difference approximation, and if we find out the delta y, so here the function value is f of x at I plus 1, and here this value is nothing but f of this location is f of xi. So the delta y is nothing but f of xi plus 1 minus f of xi, f of xi plus 1 minus f of xi, and delta x is, let's say this distance is h, so this is h, so f dash of xi is correctly given by this first expression a. Okay, so we'll go to the next question. Okay, so the next question is the condition number for the function f of x cos x, and x is given. So what we want to find out is the sensitivity here, how rapidly they or how these functions respond around this point. So the condition number is given by x f dash x fx. Okay, so x value is given, so x is pi by 2 plus 0.1 pi by 2, and we can compute this. $1.7279. Okay, and if we see f of x is cos x, so f dash x is sin x, and if we substitute in this, condition number will be x will be 1.7279, f dash is sine of 1.7279, and f of x is cos of 1.7279. Okay, so we'll compute this. So just x is equal to, we will write this one, x is equal to this value, and we want to find x into sin x divided by cos x. Okay, so condition number is minus 10.90. Okay, so this value is okay, so here the derivative will be minus, so this is minus, and it will be 10.9094. Okay, so if we see, this is the correct option. Okay, I hope this is clear. So we'll go to the next question. Okay, so next question is match the following. The first question is Newton-Raphson method. Then the first column is Newton-Raphson, Runge-Kutta, Gauss-Seidel and Simpson's rule. So you can see that now the methods are given on the left column, and the right column is the what it performs. So does it perform integration, or it's used for root finding, or for ordinary differential equations, or solution of system of linear equations. So Newton-Raphson method is used for computing the roots. Runge-Kutta method is used for ordinary differential equations. Then Gauss-Seidel is used for a solution of a system of linear equation. This is C. And Simpson's rule is used for integration. So you can see that A is associated with 2. So we'll write. So A is 2. Then B is 3. C is 4, and D is 1. So this is the correct option: A2, B3, C4, D1. Okay. So yeah, we'll go to next question. Okay. So the next question is the approximate value of 17, third root of 17 after performing 3 iterations on the Newton-Raphson method, starting with initial approximation x0, which is 2, will be okay. So what we want to find out is 17 raised to 1 by 3 is equal to x. We want to find out the third root, and we can rewrite this: 17 is equal to x cube, and that is nothing but we want to write it as f of x is equal to x cube minus 17, and if f of x is equal to 0, so at what x this is 0, will satisfy this constraint, which is 17 is equal to x cube, and that is nothing but it will give nothing but the cube root of 17. Okay. So we have simplified this equation now, and we'll use the Newton-Raphson method. So what it method tells is xn plus 1 is equal to xn minus f dash at xn divided by f of xn. Okay, so we already have f of x. So what we will do is we'll find out the differentiate it once with respect to x. It will be 3x square. Okay, so what we will do is substitute f of x and f dash of x, let's say in equation 1. So this is our equation 1. If we substitute there, we will get xn plus 1 is equal to xn minus 3xn square, and f of xn is nothing but xn cube minus 17. Okay, so what we can do is simplify this. No, I think I rewrote it. Okay. Okay, so I wrote it opposite, so it should be this way. So f of x will be up. So x cube xn cube minus 17 divided by f dash xn. So f dash we already find out, which is 3xn square. Okay, so if we do this, it will be 3xn cube minus xn cube minus 17 minus plus 3xn square. So if we simplify it, it's xn plus 1 is equal to 2xn cube plus 17 divided by 3xn square. Okay, so what we will do is we'll start with x0, which is 2, which is given in the question itself. So x1 is equal to 2 into 2 cube plus 17 divided by 3 into oh sorry, I think it's there anything. Okay, so xn square, it will be 2 square. Okay, okay, so 2 divided, so we have 3, 2 square, 3 by numerator is 3 into 2 raised to 2, so 2 into 2 cube plus 70. Okay, so this is 2.75, and if we go for x2, which is 2 into 2.75 cube plus 17 divided by 3 into 2.75 square. Okay, so we will compute that. 2 into 2.75 that is 23 plus 17 divided by 3 into 2.75 square. Okay, it is 2.5826. Okay, so now we will go for the third iteration. Now we write here itself, x3 is equal to 2 into 2.5826 cube plus 17 divided by 3 into 2.5826 square is equal to, okay, so I will just modify this equation itself. It is 5826 5826. Okay, it is 2.5713. Okay, so we have performed the 3 iterations, starting with x is equal to 2, and you can see that we have reached to this value. So we can try one thing, is we'll just take the cube of this and we'll see what is the value. So 2.5713 raised to 3. Okay, so you can see that we are getting almost 17.0004 up to almost 4th decimal place. There is error, so it is a better approximation for actual cube root of 17. So 2.5713. So second option is the answer that we will get after 3 iterations for when we are finding the cube root of the 17. Okay, I hope this is clear. Okay, so with that we will go to the next question. The next question is, the error in the measurement of the radius of the sphere is 1%. the error in the calculated value of the volume is. So okay, so we know the relation between the radius and the volume of the sphere. Okay, so the volume is nothing but 4 pi 3 pi r cube, or you can, if you don't remember this, is just nothing but some constant times r cube. So let's say this is volume, we can take the log on both sides. So log of v is equal to log of constant plus 3 log of r. And now what we can do is we can differentiate this, let's say with respect to r. So what we will get is 1 upon v dv by dr is equal to, this derivative will be 0 for the constant, then 3 1 upon r. Okay, now we will multiply throughout by dr. So dv by v is equal to 3 dr by r. And if is, so often this we take this dv and dr tendings to 0, but if they are sufficiently small, we can replace with delta v and delta r. So delta v and by v is equal to 3 delta r by r. Okay, so we know delta r by r is 1%. So 1% is 1 by 100, and if we substitute that here, it is 3 into 1 by 100, and it is nothing but 3 by 100, and which is nothing but 3%. So the volume, the error in the volume computation is 3%. Okay, so this is the correct answer, B. Okay, so I hope this is clear. Okay, now we will go to the next question. Okay, so the next question is the solution of the following system of equations will be. Okay, so we have given it is given that it is given the, so we have 3 set of linear equations, and we can use the whatever we like Gauss elimination method to find out the roots for this. We'll start with, so equations that we have is x1 plus x2 plus x3 is equal to 1, x1 plus x2 plus x3 is equal to 1, then 4 3 minus 1, 4 3 and minus 1, which is nothing but 6, 3x1, 5 3 4, x2 and x3. Okay, so these equations are given, so we can write this into matrix form, x1 x2 x3, 1 6 4, and the coefficient matrix is 1 1 1. Then for the next row, if we see, it is 4 3 minus 1, and for the last equation it is 3 5 3. Okay, so what we can use is the, let's say, consider this first element as the pivot which is 1. So r2 minus 4 r1 and r3 minus 3 r1 if we do. So the we, and also we will use the augmented matrix here. Okay, so the first row will be unchanged, if we do the subtraction, so this term, first term will be 0, so 3 minus 4 will be minus 1, and minus 1 minus 4 will be minus 5, and 6 minus 4, which will be 2. Okay, and for third row, if we see, we are subtracting 3 times the first row from the third row. It will be, the first element in A will be 0, so 5 minus 3 will be 2, 3 minus 3 will be 0, and 4 minus 3 will be 1. Okay, now what we will do is so there are negative signs here, so what we can do is we'll just multiply this equation by minus 1, 1 1 1 1 minus 2 0 1 5 0 2 0 1. Okay, so what we done is minus r2. Okay, so r2 we have changed to minus r2. Okay, so what we'll do is we have to make this element below this pivot, which is 1, to 0. So we'll subtract 2 times the row 2 from row 3. So we'll change r3 to r3 minus 2 r2. Okay, so first element row will be as it is, then next row also will be as it is, 0 1 5 0 1 5 minus 2, and if you subtract 2 times, it will be 0 0 minus 10, and if you see, this will be this will be 4 minus 4, and if you are subtracting, it will be plus 5 into, like, in 1 it is 5. Okay, so we have got this upper triangular matrix, and then here we have some modified B matrix, B vector, and we can use the back substitution. We will start with the last equation, which is minus 10x3 is equal to 5. So x3 is equal to minus 0.5. Okay, so we got x3. Now we will solve for this second last equation, which is x2 plus 5x1 x3 is equal to minus 2, and x2 plus 5 x3 we already have, which is 0.5, is equal to minus 2. So x2 plus 2.5 is equal to minus 5, sorry, here minus 0.5. So this is minus, since it's minus 2. Okay, so x2 is equal to, this will go on this side, and then it will be plus 2.5 minus 2, which is 0.5. Okay, so we got x2 also, and finally we will solve for this equation, which is x1 plus x2 plus x3 is equal to 1. So x1 plus x2 plus x3 is equal to 1. x3 we already found out, minus 0.5. x2 is also, x2 is 0.5. x1 is equal to 1. So these two terms are cancelling with each other, so x1 is equal to 1. So x1 is 1, x2 is equal to 0.5, and x3 is equal to minus 0.5. Okay, so we have the answer. So it is so C is the correct answer. Okay, so we will. I hope this procedure is clear, and you might have used it in the previous assignment. So with that, we'll go to the next question. The order of convergence of the regular fuzzy method is. Okay, the answer is, in short, it's one, but we'll see how it comes to be one. Okay, so if you see the method, let's say this is x0 and this is xk, and this will be xk plus 1. So here we will fix x0, and then iteratively we will go on determining the xk plus 1, and you can see that this is there are two similar triangles, so we can say this is f of xk, and this is nothing but x0, and this value we will say f of so this point is nothing but x0, f of x0 and this point is nothing but xk comma f of xk, and then you can see that this triangle, just change the color, so this triangle is similar to this triangle. So what we can write is, so we'll write the ratio of this length and this length, that is nothing but f of x0, and the function is negative, so to make it positive we'll write f of xk, and now this term in the denominator is positive, and then we'll write this length, which is x0 minus xk plus 1, and next we will write this the length, which is xk plus 1 minus xk. Okay, so after doing this simplification, what we will get is xk plus 1 is equal to xk minus xk plus 1, so minus x0 divided by f of, let's say I will say k only, or this is nothing but let's say f of k minus f of 0 fk. Okay, so what we want is, let's say x, so let's say this is the root, and okay, so this is the root, and we'll say this is nothing but xi. So if xi is the root, so f of xi is equal to 0. So we know this. Okay, so what we can say is, let's say x k is equal to xi plus the error in the root at kth iteration, and x k plus 1 if we do the next iteration, there the error will be epsilon k plus 1. So what we want is epsilon k plus 1, it will be some order of some constant in epsilon k and raised to p. So we want to find this minimum value of p, or the order of p, that will give the order of convergence for this. Okay, so we will we have this equation, so we will substitute these values for xk and xk plus 1. So that will be xi plus epsilon k plus 1 is equal to xi plus epsilon k and minus, so this will be xi minus epsilon k minus x0 will be xi minus epsilon naught. So this is some constant offset, then fk, so you write fk as it is, minus f0 and fk. Okay, so this term will get cancelled here, this also will get cancelled here, so we can see epsilon k plus 1 is equal to epsilon k minus, so okay, so here we left with epsilon k. So let's say take this minus out, so it will be plus epsilon k and minus epsilon 0, fk minus f0 fk. Okay, so if we see fk, which is nothing but f of xi plus epsilon k, it will be f of xi plus epsilon k f dash at xi and so on, or we can write some more term by 2 f double dash of xi plus dash dash. Okay, so we know that this is xi is the root, so it will be 0, then epsilon k f dash of xi plus epsilon k square by 2 f double dash of xi. Okay, so this is fk and f0 is anyway constant, so we will not bother much about this. So f0, let's say some constant, we'll say beta. So we will substitute these values. Epsilon k plus 1 is equal to epsilon k plus epsilon k minus epsilon naught divided by okay, so we write this term instead of fk, which is epsilon k f of f dash of xi plus epsilon k square by 2 f double dash xi. Okay, and then higher order terms are neglected, or we can just put dot dot, but it doesn't affect our solution. Okay, so in the denominator also fk is there. Second. Okay, so it will be epsilon k f dash xi plus epsilon k square by 2 f double dash of xi. Okay, and minus beta, let's say, which is nothing but f0. Okay, so epsilon k plus 1 is equal to epsilon k plus epsilon k minus epsilon naught, and from this term okay, so from this term we can take out the epsilon k outside out common, so it will be epsilon okay, so it will be epsilon k, and it will be f dash xi plus epsilon k by 2 f double dash of xi, and yeah, divided by f dash of xi plus epsilon k into okay epsilon square by 2 f double dash of xi minus beta. Okay, so epsilon k plus 1 is equal to epsilon k plus epsilon k minus epsilon naught. So this term we can so this term we can just treat this others as constant. So let's say this as alpha 1 plus alpha 2 epsilon k divided by, we'll take this beta common, so it will be beta, or we can take this minus beta outside, so it will be 1 minus epsilon k, and then this also we can treat as a constant. So let's say this is beta 1, or we can include that minus sign inside, and it will be plus beta 2 epsilon k square. Okay, so eventually what we will get is 1 minus epsilon k, and here we can neglect this term, so it will be epsilon k minus epsilon naught. So we are just trying to minimize, or like we are finding the minimum epsilon k that remains on the right hand side with minimum power. So alpha 1 plus alpha 2 epsilon k, it will be beta, and it will be 1 plus beta 1 epsilon k inverse, and okay, so epsilon k plus 1 is equal to epsilon k minus epsilon k by beta epsilon k minus epsilon naught alpha plus alpha 1 plus alpha 2 epsilon k, and this one if we expand this, and we'll neglect the higher terms, order terms, so this minus sign will appear in between, so we'll just consider the one term in the expansion, that will be 1 minus beta 1 epsilon k. Okay, so so what you can see is epsilon k, if we take common from this equations, it will be 1 minus epsilon k minus epsilon naught beta alpha 1 plus alpha 2 epsilon k 1 minus beta 1 epsilon k, and we can just say this is approximated, so this will be epsilon k, and this whole can be expanded as one, like if we simplify it will turn out to be a1 plus a2 epsilon k plus a3 epsilon k square, and so on. So we are just neglecting this higher order terms, so it will be some a1 epsilon k plus 1. So we can see that this power which is 1, so this power is 1, so that's why this order of convergence is 1. Okay, so okay, so this is the, so this power is 1, so that's how the order of convergence 1, and this is the correct answer is already we have defined, we have already given the answer, but In order to exactly find out this convergence, order of convergence, we have to go through this derivation. Okay, so I hope this is clear. Next we'll go for another question. Okay, the approximate value of this integral using midpoint method will be. Okay, so what we have to find out is integral 0 to 1 sin x upon x dx. Okay, and okay, so let's say whatever the functional form this has, but in general let's say that there is some function. Okay, we'll just draw some random function. Okay, so let's say this is the function itself, and this is a, this is b, and this is the location, which is, let's say, x mean. So x mean is nothing but the central location. So what we can do is we can approximate this function to be uniform by this value. So this value that we are assuming is nothing but f at xm, and to get this area under this curve, and this area under this curve we will approximate as the area under this actual curve. So this area, the red area, we will approximate by the blue one. So anyway, there exists an error, but okay, that's fine. Okay, so you can see that we are just interested in determining this mean value or the function at mean location. So if we say f of x is nothing but sin x upon x, and a is 0 and b is 1, so the mean location will be a plus b by 2, which is nothing but 1 plus 0 by 2, which is 0.5, and f at 0.5 is nothing but sin 0.5 divided by 0.5, which is nothing but sine of 0.5 divided by 0.5, which is 0.9589. Okay, and you can see that whatever approximation we have made is nothing but the rectangle. So the integral can be approximated as mean into this delta x. So let's say this is the delta x, and delta x here is, so delta x is equal to b minus a, which is nothing but 1. So we already find out the mean value of the function at mean location, and delta x is 1, so the answer is 89. Okay, so so this option matches, and that is the correct answer. Okay, so we'll go to the next question. Okay, the convergence of the Newton-Raphson method is linear, quadratic, cubic, or quaternary. Okay, so we can do the same exercise that we did for the regular falsi method. So in the Newton-Raphson method, xn plus 1 is given by xn minus f of xn divided by f dash of xn. And what we are so let's say this is the function, and we are saying that at this xi is the root, so f of xi is 0. Okay, and xn plus 1 is nothing but xi plus error at, so we are expecting the root should be xi, but there is error at nth iteration. So at nth iteration that error will be xi plus epsilon n. Okay, so if we substitute this here, it will be xi plus epsilon n plus 1 is equal to xi plus epsilon n minus let's say this is fn f dash at n. Okay, so this xi and xi will get cancelled, so epsilon n plus 1 is equal to epsilon n minus fn f dash n. Okay, so fn is nothing but f at xi plus epsilon n, so that we can expand using the Taylor series. So it will be f xi f dash at xi into epsilon n plus f double dash xi by 2 factorial into epsilon n square. Okay, and we know that this is the root, so it will be 0, so it will be f dash xi epsilon n plus f double dash xi by 2 epsilon n square. Okay, so we will expand for this also. So epsilon n plus 1 is equal to epsilon n minus fn we got to be f dash okay, so f dash of xi epsilon n plus f double dash xi by 2 epsilon n square. Okay, you don't need to do all this, but in just to for as an exercise you can try out how to compute the order of convergence. Okay, so f dash n I'll just expand it here and then write into f dash xn is nothing but f dash xi plus epsilon n, and which is nothing but f dash xi plus f double dash of xi by 1 factorial into epsilon n. So we will substitute that here, f dash xi plus f double dash xi into epsilon n. Okay, so this is the equation that we have, and we can proceed and simplify this how we perform for the regular fuzzy method. So epsilon n plus 1 is equal to epsilon n minus, and this term is common, so we can divide by numerator and denominator by this term, so it will be epsilon n minus f double dash xi by 2 epsilon n square and f dash xi, and 1 plus f double dash xi into divided by f dash xi epsilon n. Okay, so what we'll do is we'll this whole term okay, so this whole term we will consider to be C star, let's say. So it will be epsilon n plus 1 is equal, or we'll say just c1, it will be epsilon n minus c1 epsilon n square divided by 1 plus so it will be 2c1 epsilon n. Okay, so epsilon n plus 1 is equal to, and here we have neglected all the higher order terms, so instead of equality we can just say approximated. It is the epsilon n minus, we can take epsilon n common here, epsilon n 1 minus c1 epsilon n and 1 plus 2c1 epsilon n inverse. Okay, so epsilon n minus epsilon n 1 minus c1 epsilon n, and this is we have to compute the inverse, and we'll just neglect the higher order terms, so it will be c1 epsilon n. So it will be epsilon n minus epsilon n 1 minus c1 epsilon n minus 2c1 epsilon n minus plus 2c1 square epsilon n square. Okay, so if we see epsilon n minus epsilon n plus c1 epsilon n square, there are two terms. So this c1 and 2c1 is it, okay, so it will be minus 3c1 minus 3c1 epsilon n square, and this minus plus. Okay, and this will be minus 2c1 square epsilon n cube. So this term will get cancelled, and this is 3c1 epsilon n square and some higher order terms. So you can see that the first leading order term is epsilon n square, so the order of convergence, let's say p is equal to 2. So that's how this order of convergence is 2, or that is nothing but quadratic. So the order of convergence for Newton-Raphson method is quadratic. Okay, I hope this is clear. So we will go to the next question. Okay, so the next question is the function fx is equal to sin x is approximated by Taylor's polynomial of degree 3 about the point x0. Find c, so we have to find out the c value such that the error satisfies this constraint. So the error should be, so we are approximating by third degree polynomial, so the error associated is r3, and it should be less than 0.001 for all x in the interval 0.0, c. Okay, so if we are let's say this is f of x is equal to sin x, and if we approximate it with the third degree, what we want is that error associated should be less than 0.001. And okay, so if we expand it, f of x is equal to, and one more thing is we are expanding it about the x equal to 0. So f of 0, so this is nothing but the Taylor series expansion, f dash 0 x by 1 factorial plus f double dash 0 x square by 2 factorial plus f triple third derivative x cube by 3 factorial plus r3. So this is nothing but the residue associated. Okay. So this residue will be residue we have to find, like we have to constrain this residue to be less than 0.001. And if we see f of 0, which is nothing but sine 0, which is 0, f dash of 0 is nothing but if we take the derivative, it will be cos nothing, so that will be cos 0, it will be 1. So f double dash 0 is nothing but we have to differentiate this again, so sine of 0 will be 0, f triple dash of 0 will be minus cos of 0, and that is nothing but minus 1. So we have this expansion f of x is equal to 0, or we will, okay, so we will keep this anyways 0. So f dash 0 is 1, it is nothing but x plus 0. This f triple dash is minus 1, so minus x cube by 3 factorial, and the residue term. Okay, so the residue for this expansion will be x minus x0 raised to, so we are having this third third degree polynomial we are using, so it will be, so in general I will write and then we'll substitute this r3 specially. So if it is nth order polynomial approximations, the root will be the error term associated will be of this form. N plus 1 xi. So this xi will be in the interval. So let's say we are having this interval 0 to c. So xi will be somewhere in this interval. Okay, so now we are approximating with third polynomial, and then x0 is 0, so it will be x raised to let's say 4. So n is 3, so 3 plus 1 is 4, and 4 factorial, and f 4 and here, okay, xi. Okay, so if we just see here f let's say fourth derivative is nothing but minus sine x. Okay, so we already computed the third till the third order. So here if we go one step further and compute the fourth order derivative, it will be minus sine x, and if we substitute here, it will be x raised to 4. 4 factorial is 24, and it will be not 4, it is fourth order derivative. Okay, that is minus sine x. Okay, and we are not x but xi. Okay, so what we want is r3 to be less than 0.001. So we'll put this constraint on this, x4 by 24 minus, so this minus is minus sine xi. So this whole term should be less than 0.01, and what we can for all the x we want to for all the x we want to constrain this, what we can do is we can say that maximum of x4 by 24 for x in between let's say 0 to c is our interval, and also maximum value of sine xi over the same interval. If we take the multiplication of this two term, it should be less than 0.001. So if we see this term which monotonically increases or continuously increases with c, so the maximum value of this first term within this 0 to c interval will be c raised to 4 by 24, and maximum value of sin I is anyway, even it is within interval or not, it will be always 1, so we just substitute that value as 1 and it should be less than 0.001. So we got c raised to 4 by 24 should be less than 0.001, so we can see c4 is less than 0.024 and c should be less than 0.024 raised to 1 by 4. So we will compute this value. Okay, it is 0.3936. Okay, so we can see here this is closely matches with the answer that we got. So this is the correct answer, and with I have prepared these questions. So yeah, so this is all for today. If you have any questions, you can ask me mostly now in the next lecture. So we'll stop for today, and yeah, you can go through the lecture, and if you have any doubts, you can ask me next time. Okay, yeah, thank you.